Uh, yeah, so shall we start, I guess? Um,
Yeah.
okay. Um, so is there anything you'd like to review briefly? Um, I think we probably, what did I do? Okay, and then. I did not do that and then. Um, but yeah,
Yeah.
so last time we were making the list, and I think the last thing we did was we made this tail method. Um, right, which returns the tail of the list. And there were a bunch of shenanigans here. So we have solve.head, which is an option of an RC of a node, right? But we actually want an option of a ref of a node because we don't want to own this thing at all, right? Remember when I showed
Mhm.
that diagram um, with the, uh, where is this? Oh, it must, let me bring it up on Discord. Um, Here. Okay, I don't like that. That's just a link to Excalibur.com. Oh, no, no.
Oh
Okay, yeah,
no,
yeah.
for me it's loading.
It worked. Yeah, yeah, yeah. I don't know what's going on. Oh, no, I see. It was a weird, it was shenanigans. Not important. Right. Remember when I did the thing that had the unnecessary increment and then decrement when we were still
Hmm.
grabbing the RC, so we don't need that. Oh, boy. We don't need that. So we do this dot as ref, and then we map, and then we clone it, and then we flatten it. And apparently dot and then is equivalent to that. Let's look at that, because it's good to know that there are lots of these little methods on option that can be exactly what you want, though it's also, possible um, to get lost in the weeds. So do you remember what flatten did?
Right, so basically decrease the amount of options,
Yeah.
nested options to one. So
Yeah, so there's also a flatten method. Maybe there probably is on either on iterators or on what is it? Or on vectors in Rust. Um, flatten is, I think, more intuitive to think about on on lists of things, because the idea is if you have a list of lists, then it makes a lot of sense. You could just flatten that into one big list. Like, take the contents of the first list in your list of lists and concatenate it with the next and the next and the next, and then you end up, with one big list, right? Um, so that's effectively what this is doing, except these are lists. Like each option, you could think of it as a list of 0 or 1 things, you know?
okay.
So if both of these are sum, we end up with some, but otherwise, uh, we end up with none. Yeah, you're totally right. So what's this dot and then? Well, let's look in the docs. Um, I don't know if you were here when I showed this, but I love showing this. If you installed Rust with RustUp, which is the right way to do it, then you can do RustUp doc, and it opens this local file that gives you a bunch of this stuff. And you could also, I think, do RustUp doc dash dash std and go straight here, which is the Rust standard library. And again, this is just a local file, so even if I didn't have internet, it would work. And this is just all of the documentation for the version of Rust that you have installed. Okay, so let's look for and then. Oh, it's right here. Okay. Um, so let's just look at this. Let's ignore this. This is actually, it's more readable if I shrink it, right? This is just like something over to the side. It looks like it's part of it at this precise zoom level, but it isn't. So this is just and just takes self, so the current option, and an option, another option of a potentially different type. So this is U, not T, right? It's an option of T. You can see like here, unwrap returns T, unwrap or returns, everything. Option is defined as option of T, right? But and takes a potentially different kind of option, and it describes it pretty simply. Returns none if the option is none, otherwise returns opt B. So that's actually not what we want, because what it says is arguments passed to and are eagerly evaluated, which is just the normal way arguments are evaluated. It's kind of redundant. What that means is, like, in order to call this, first we figure out what opt B is, right? There's some expression that we put after the comma, or not after the comma, we put in the parentheses, right? When we do dot and something, and that is evaluated to an option, and then we call and, right? Let me, hang on 1 second. Let me close my stream. I don't need to be seeing that. I would rather look at you. Okay. So I can see whether you're getting things. But what we want to do is we want to give it a function to call. We want to give it a lambda. We want to say, if self.head is something, then map it to n.next.clone so that we get the tail, right? So this is just an alternate way of doing this. Map does this, but then we end up with two options, right? Because we clone n.next.clone, because n.next is an option, and then we have to flatten it. Dot and then does something a little differently. Dot and then explicitly takes a function where the function implements the trait fun once, which is a fancy trait for functions. This means it's a function that we can call once. And it's unintuitive maybe why we need a separate trait for a function that we can call once, but it's because Rust is manually memory managed. Or it's because of Rust's rules around memory management. I'll get to that in a second. But first, I just want to cover overall how this works. So f is expected to be a function explicitly that returns an option, again, of some other type. In our case, they're of the same type, right? We're just dealing with RCs of nodes. But what does this do? It returns none if the option is none. Otherwise, it calls f with the wrapped value, so with t. So it works like map in that way. It calls f with the thing inside our current option, right? And returns the result, which is interesting. It returns the result of f, this option of u. It doesn't, like this is the return value of and then. So it does the flattening for us, basically. How should we think about and then? It says, if this option is sum, then run this function and give me its result. Otherwise, give me none. But the way it works is it gives you none of this new kind of option. So it also potentially changes the type. It potentially returns something of a different type. In our case, again, we're returning the same thing, but that's how it works. That's how it avoids the need for a separate flattening step. I guess the broader pattern here is that there are actually a lot of methods that are going to be like and, which kind of makes sense. And is, we're saying if both of these options are true, give me the second one. I guess that giving me the second one is weird, but that's just how it works. But then there will be methods like that, and then there will be methods that are named the same sort of mathematical term, and then. And the methods that end with then will instead take a function that they call. So the value of this is that we can do things with the wrapped value in this function. So we can do things with the option that with self, right? But with self having been unwrapped. So let's look here, right? She runs and then, and this is a node. This isn't an option of a node anymore. So that's an advantage of having this function is it takes this, it allows us to mess with the thing inside the current option. It says, you know, we're only ever going to be calling this function in the sum case of the thing that we're doing dot and then on, right? We're only going to call it if it's in the sum case. So then we have access to the thing inside. And this function only runs, you know, in this case, that's the main value. But the other value is, even if we didn't need access to the thing inside our current option, this means this function only runs if the option over here is sum, which means it's effectively lazy evaluation. We're delaying the evaluation of the thing that this will turn into. This function doesn't run otherwise. Contrast that with just and, which we always figure out what this opt b is first, because it's just an option. We have to calculate its value first. Here, because we're giving it a function, we can delay the computation until whether we know it's necessary. So this is sort of short-circuiting, right? If we do none dot and then something, right? None dot and then we pass it a function, the function will never get called. Because it knows that the left side of the and is none, is false in some sense, right? So we don't end up calling that function. Is that making any sense? I see you sort of questioning things.
Yeah. It just is it kind of computationally less expensive than just passing down an option, and well, technically, what I mean is, then is it less computationally expensive than what we did before?
No. So it's with this exact sort of code, like code that's super micro, that's super small, the optimizer is going to be awesome at figuring everything out anyway. So like it looks like we're calling a bunch of functions, but they're all really short. Like, what's the definition of map? Map just matches self. If it's sum, it calls f of x and it returns sum, right? So this is tiny. It's going to get inlined. Flatten is also going to get inlined. Flatten is just, if it's sum, then return what's inside that. The magic of flatten is that it, apparently they, okay, never mind. Apparently they want to rewrite flatten with and then. I don't know. This is whatever. The magic of flatten is entirely the fact that it is only implemented on option of t. So that's how all it has to do is get the thing inside it, and that is the option of t. So that's all we need. So anyway, the point is these methods are really small, so the optimizer is going to inline them, and then it's going to consider the whole function with all those things inlined as one thing, and it's going to be really smart, and it's going to, you know, optimize the hell out of it. And it's going to do that in either case. So this is really just a, you know, it's nicer for us, I guess, but if you don't want to do it, it's fine, to think about this as a little bit of a simpler pattern of saying, if we have a head, then clone its next and give me its next. But what you were saying, computationally more expensive. So it's not computationally more expensive or less expensive than what we were doing, but relative to and, it depends. Because in the with and, if it's expensive to compute this other option, then we probably want to do and then. Because with and, this other option gets computed no matter whether we need it, right? We compute it before we call and, because we have to pass it the actual option. But here we just pass it a function that returns that option. So it's only going to call this if the thing to the left of the dot, the thing we're calling and then on, if that is sum. That's what I mean by this is eagerly evaluated, and then this sort of lazily evaluates the option it might return. It lazily does it because we don't give it the option itself, we give it a function that'll return the option, and then it only calls that function when it needs to. Does that make sense?
Yeah.
This eagerly and lazily evaluated stuff is terminology that applies better to other languages like Haskell. Haskell actually is by default lazily evaluated, so it doesn't compute anything until it's needed, which is only like even workable because Haskell is purely functional by default. In Haskell, the only thing that functions typically do is return something. So they don't do side effects. So you shouldn't care about what order things run in. So the compiler can safely optimize with, at least with those functions. I'm not clear on all the edge cases, but it can safely optimize and delay evaluating them until the last possible moment. But that's also, like, there are trade-offs. You can end up with code that looks like it should be fast, or should be reasonable in terms of memory usage, but because it's lazily evaluated, what it actually is going to end up doing is delaying all of those computations and keeping track of them in memory, and then your memory footprint can explode in Haskell when your code doesn't even look like it should. Because if you're looking at it and you're thinking eagerly, you're thinking, I'm going to calculate this, and then this, and then this, it looks like, oh no, this is simple. But Haskell is like, well, I don't actually know if I need that, so I'll just write it down somewhere, in memory, that I need to calculate that later. And in the end, it has like this giant stack of things to compute, and it blows up. That's a total aside. I do want to describe this, though, because I assume this is a source of some confusion, right? Why the fuck is what the hell is going on with fn once, right? Okay, so let's see how this works. Okay, trait fn once is the version of the call operator that takes a by value receiver. Okay. Receiver is a good term to know in programming language design. Receiver is the word that I kept reaching for but was avoiding because I assumed you didn't know it yet. Receiver is the word for the thing to the left of the dot when you're calling something. If you're doing x.foo, x is the receiver. And the reason why we call it that is because when we were initially thinking about object-oriented programming, one of the ways people were thinking about it was message passing, was the notion that you had an object X that you were telling foo. Foo was a message. So in this case, X was the receiver of the message. So this says the version of the call operator. Okay, the call operator is just, I guess it is an operator in Rust. They're claiming it. The call operator is just calling a function. So what they're saying is this trait represents, like if something implements this trait, that means it is a function that you can call. And that is, typically you don't create structs yourself that implement fn once. In fact, I think you might be unable to. But what you can do is you can create lambdas. And this lambda definitely implements fn once because well, this works. In fact, it was just showing me, yes, it implements fn once. It takes a reference to an RC of a node t, which makes sense because that's what we were doing here, because we did .asref. I wonder, anyway. And then, yeah, so this definitely implements fn once. Okay. But why once? So the secret to once is that it says it takes a by value receiver. All that means is that this is self, not amper self or amper mut self. What's important to think about is that the receiver here is the function. It's not the arguments of the function. The receiver is the function itself. So what this means is that if your function implements fn once, what that means is that we can call it once, because calling it hands the function over to this call once method, and Rust is move by default, right? It's not copy by default or pass by reference. We move our function into this method, call once, and then we don't have the function anymore. So all implementing this trait gives us is the ability to call it once. It's like how if you have a function that takes a box, then you can only give it the box once. Does that make sense? So that's why this self corresponds to only being able to call it once. But if we look at this, I'm actually not sure. Does this make sense to call multiple times? I'm not sure. Let me think. Yeah, I think this function is totally fine to call multiple times. And the reason is that this function doesn't actually capture anything from its enclosing scope. So have you heard of lambdas and capturing at all? Maybe a little? Or maybe not.
I mean, I'm familiar with lambda functions, but capturing
Okay.
not really.
So let me think of a simple example. Pun. I accidentally wrote pun instead of pub fn. Anyway, let's keep it simple for now. No, let's make it a tiny bit more complicated. So I have this, I'll call it b. And I have this function. It's going to take x, and what it's going to do is it's going to return x plus star b. Okay, let me do that so that everything works, maybe. That needs a type annotation. Function foo is never used. Okay, that's fine. Okay, so this is interesting. That is interesting. Wait, how does this work? Oh, no. Okay. First of all, this is, okay. Languages like C, or let's just use C as an example. C does not have lambdas. That means two things. That means that you can't, you don't have a syntax for this. You have to name every function, right? But the more meaningful thing is that your functions can't capture things from their enclosing scopes. What that means is if I'm writing a function in C, I have to write that function at the top level. So it can access its local variables, and it can access its parameters, and it can access globals. But it can't access local variables of other functions because it's outside of every other function, right? By top level, I mean like in a file, not inside another function, right? Every function has to just be all the way to the left and not inside any other function in C. Does that make sense? Yeah. But here, lambdas let me write functions inside other functions. And these functions can refer to data of their outer function. This function can refer to b here. this does type check. If I call f with 5 and whoops. No, let's give it 6 for whatever. So it's different number, whatever. Okay, so, and then what was the trick that I was using that was so stupid? It was like, let's make a test that then always fails. Right, so this is just so that I can run foo. Whoops. That's whatever, it doesn't need to be public. If I do cargo test, this doesn't work. Oh, foo, what's going on? Oh, I need to import it in here. No. I always forget. Let's use everything. Okay. And then this needs to be marked test. Boom. Okay. Cargo test. That one's going to fail. We see 11. And then we see always fails, so we see output. So that's this test, right? 11 makes sense because we're calling f on 6, and then 6 adds that to 5. And then f adds that to 5, right? Then we print that. Does that make sense? But what's clever here is we're capturing B. Let me think how to think about this. F has access to B. I'm not entirely sure how this works. I have to review this. But let's do that just briefly. No, I bet it's in here. Okay, capture. FN once is implemented automatically by closures that might consume captured variables. Okay. As well as by all types that implement FN mute. And FN. Okay. So what's going on here is that F actually, this function actually implements Fn. So let's start there. Fn is maybe what mathematical people think of as a function, because it's just a function that this is some crazy syntax, don't worry about it. This is like inside the compiler, this is like a super ad hoc, but what is important is that this takes self, so this takes the function by immutable reference. So that means we can, if something implements Fn, then we can call it any number of times. Because we can create as many shared references as we want to this thing. And then it also, takes the arguments, and then it returns whatever it outputs. And they say it's the version that takes an immutable receiver. Instances of Fn can be called repeatedly without mutating state. So that makes sense here. F can be called repeatedly, even though it captures this B, without mutating state. F doesn't change anything. Okay, but I don't think I've even described what capturing means exactly. Capturing means in order to use F, we have to still have a reference to this thing. So F is actually a struct internally in memory. F is like, there's a block of memory for F, right? That block of memory doesn't just contain a pointer to this function. It actually contains a reference to B. Because if I had like a different function, let's see. let's do this. Foo takes B and then creates F, and F captures this parameter B. So I can call foo multiple times. Now I have to give it, a box, right? I can call foo multiple times, and in each call to foo, I've created a different F. F does a different thing to its input. It takes its input and adds it to whatever B is in this current call of foo. Which means that even though I just wrote let F once, there are actually potentially infinite functions that I create this way. Like there's a different version of the function for each time I call foo, because I give it a different box, or I might, right? So what constitutes F is not just the ability to call this little bit of code, but also to have a reference to B. So in order to have F, we need to still have a reference to B. I think what Rust is doing here is it's realizing that we're not changing B at all. So all this F does is it actually keeps a reference to this box. It doesn't have the ability to mutate it. So that means this function is safe to call as many times as you want, and the result on the same input should always be the same, because it's not changing anything internal to itself. It's just, you just give it a function. Like if I have a given version of F, and if I pass it 0 and it gives me 5, then if I call that same F again with 0, it should still give me 5, because clearly what it's doing is it got a value of 5 for B. But I can change this so that now what it actually does is each time it adds 1 to B. Okay, this is a problem because I said because this B is implicitly immutable. It says consider changing this to be mutable. This is a bit of syntax that might be unfamiliar, but you can actually make parameters themselves mutable, just like you can make variables mutable by saying mute. So now the box is mutable, and now we have a different issue. Calling F requires mutable binding due to mutable borrow of star B. Okay, what the fuck? What's going on here is that when I call F, it changes the value of B. And B is in some way internal to F. Like B, once I created F, B is now either itself part of F or a reference to B is a part of F, and it'll change B. So in order to call F, if I remove this, we're fine, but it's silly. In order to call F, though, this has to be mutable as well, because calling F changes F. If I call F multiple times, it'll give me different things now, even with the same input. If I do this, whoops. If I do this, the first time we'll get, now let's just call foo on box new of 5. Okay, so 5 plus 1 plus 6 is 12, right? But then the next time it'll be 6 plus 1 because it changed B, and we have one version of B. I would recommend, I'm not going to spend more time on this because I want to get to the lists again, but there is documentation in Rust. I think maybe the Rust book talks about closures better. Yeah, I think this is probably a better thing to look at. But it changes B, so f of 6 this time will actually be, the first thing it does is it adds 1 to 6. So B was originally 5, but then we added 1 to it, so it became 6. Then we add 1 to 6, so now it's 7 plus 5, which is 13, I think. No, 7 plus... is, no, 7 plus 6. Wait, how did I get 12? Hang on. 6 plus 1. No. 5 plus 1 is 6. Okay, and then we add it to 5. So actually that's 5 plus 6 is 11. So the first time it'll print 11, and then the next time it'll print, no. What am I doing? No. First time it'll print 12, because B will be 6. My bad. B will be 6. Then we add it to 5. And the next time, B will be 7, and we add it to 5. No, B will be 6, and we add it to 6. That's 12. That's my problem. And the next time, B will be 7, and we add it to 6. That's 13. I was getting it all confused. I'm sorry. That was just me struggling to do math. But yeah, so now we see 12 and 13. 12, are you following, sort of? I know that was in the weeds. But yeah, okay. So if you're curious about this stuff, I would encourage you to read this, which I think is going to be a lot more useful than my very silly example. I will put a link to that right in here. But what's important to know, I will just finish this. Oh, that's not going to help. Nah, I'll just say that. What's important to know is that some things actually don't just capture things mutably, they capture things by owning them. So if I instead just make this a very simple function that returns x, but first I drop b. So drop is a function that just takes whatever you give it and calls its destructor. Drop is like, delete this now, please. So now this is a function that I can only call once. And in fact, the second call of it is an error, because this calling of it moved the value. Because, maybe not because, but that's connected to, this isn't the root cause, but that's connected to the fact that because it only implements fn once, its call function, this is the thing that actually happens when we call it, takes self by value, which means it takes it by move, so we can't call it multiple times. Why is this necessary? This is because in order to call this, B has to exist. Once we call it, B no longer exists. We dropped it. So this F now literally owns B. It doesn't just have a mutable reference to it because it has to drop it.
Okay.
So we can only call it once. And that's why fn once exists. It's so that we can write things like this. Also, we don't need it to be mutable anymore, because what's actually going on is that f is completely taking ownership of b. We don't need it to mutably reference b, and it owns. I think what's actually going on is it's not modifying b. I'm actually not totally sure what's going on. But whatever, we don't need it to be mutable. I guess it doesn't really matter whether it mutates anything or not, because as soon as you call f, it's invalid. You cannot call it again. So why was fn once the thing that was in here? Why does and then take fn once? It's because it can. I don't actually understand this plus destruct, but it's because it can. Because and then on an option is going to call this function at most once. because an option only ever holds one thing or zero things, and then calls this thing if this thing is sum, and it only calls it once. So this is the most flexible way of writing the type of and then. So we can give and then functions that you can only call once because they own something and then drop it. Frequently in Rust there, or I guess more generally, but often in Rust, there are things that work like this where you want your function to be able to take as many possible parameters as it could. So you have to pick, you should pick the broadest possible type. And also importantly, everything that implements fn or fn mute also implements fn once. Because fn and fn mute are things that you can call multiple times. Fn mute is something that you need to have a mutable reference to call it. But fn doesn't modify anything. You can just call it even if you just have a shared reference. And implicitly, that means you can also call them just once. So fn, the way that this is modeled in the type system is that Rust actually has something kind of like inheritance, which is this super trait shenanigans, which is where fn mute, everything that implements fn mute also implements fn once. That's what this colon syntax means. So it's sort of like fn mute inherits from fn once, except these are both traits. So it's like an interface implementing another interface in Java. That's what this is saying. This is saying this trait, in order to be fn mute, you also have to be fn once. And if we also look at fn, everything that is fn is also fn mute. If you have something that you can call multiple times with just a shared reference, then that is also something that you can call multiple times with a mutable reference. It's fine either way. So fn is a subtrait of fn mute, which is in turn a subtrait of fn once. So there's this hierarchy. That was kind of off the rails. I just want to cover something small that actually has to do with linked lists. First I will take a drink though. Okay. Now that we have tail, we should probably provide head, which returns a reference to the first element. Yeah, because right now we can't actually observe the contents of our list. We can just add things to the beginning of it and then look at its tail, but that is also a list. So we need to be able to observe like some element in the list. So this is pretty simple. Pub_fun head takes amperself, because with this immutable linked list, we're never modifying anything. So it's safe to share, so we can always take amperself. So no, this does not return self. This returns t, because it returns the thing inside. Okay, so we want to call self.head dot, and then head is a link, which is an option. Okay, so I think we want to map it. Okay, so we can't return t. We have to return an option of t. And actually, we have to return an option of a reference to t, because we're not trying to destroy what's inside our list. We're trying to return a reference to the head. And this is the nice way of doing it. I guess we could do a reference to an option of t, but then, you know, that's messier. It's nicer when you have we could return a reference to an option of t because it happens to be that we store options of t. Oh, no. We couldn't return a reference to an option of t. We could not do this. Whoops. We could not do this because we don't store options of t. We store options of RC of nodes of t. So there's no option that we could return a reference to. We need to return an optional reference to t. We do store t's all the way in the node, but we don't store options of t. There's all this stuff in the way. That might be overly complicated, but the key thing is when you're writing an API, if you want it to sometimes fail, you should write just a bare option of something. You shouldn't write a reference to an option because that's exposing a reference to your data, right? We want to give them, or that's exposing a reference to more of your data than you have to. Here we do want to give a reference to our data, but only the item. Okay, so self.head.map. We have some node that is our head, and then we just want to give it the element. That's all. And I think that this will not work. Yes, this does not work for some reason. Cannot move out of self.head, which is behind a shared reference. Okay. At this point, I think we understand what's going on here, or somewhat. What's going on here is that self.head is an option of an RC of a node, and we have not convinced Rust that we want to access the node inside. It's trying to just deal with the whole RC. So we need a reference to this RC. So we do .asRef. Or no, we need a reference to the node inside. And now it's all happy. So now we have an option. Okay, T equals reference to RC. So this is actually weird. It's a reference to an RC, and an RC is itself a pointer. So this is two levels of indirection, which is silly. I'm sure the optimizer will figure it out. But that's what's going on here. And then we just return a reference to n.element. Okay. The compiler is, again, hiding fancy stuff from us. It's doing lifetime elision, because what's going on here is we're returning returning a reference to our data, which means that when you call this function, you then have a reference into the list. So if we then dropped the list, we can't keep this option around anymore, right? Because we would have dropped the thing that it's referencing. So what's going on is something like this, I think, except we also need to bring this in. But that's something that the compiler will figure out for us. This just means that we're returning something that only lives as long as self. And then I'll just copy her test case. It's very basic. We just create some lists, and then we make sure that the items work out correctly as you generate more lists based on them. Let's make sure that no more than 2 tests fail, because I have 2 tests that are intentionally failing. 8 passed, 2 failed. Okay, we're good. I'm also going to go through iterator. Okay. Iter is also identical to how it was for a mutable list. Yeah, so iterator still iter, our by reference iterator, still has an option of a reference to a node internally. It's just that in our list, it's now the node is now in an RC instead of being in a box. And then this is very redundant, and it's fine if you have trouble following it. But what this does is if our current next is sum, then we advance our next and we return our old next's element. So this node is what was inside self.next. So first we advance our self.next to its next, right? And then we return a reference to what was our next. So the first time you call this, our next was the head of the list. And then the next time it's one into the list. Okay. This .asDref is calling a different function than it did before. It's calling .asDref on an option of an RC, not on an option of a box. but it still does conceptually the same thing. It turns that option of an RC into an option of a reference. It says, what would happen if I dereference the inside of this option? Well, you would end up with a reference to the inside of the option first. So that's what .asDref turns this option of RC into an option of box. Let me just copy that code and show that with the what's going on here. Self.head is an option of an RC, but then next is an option of a reference. In our second list, we also did self dot was I saying head? I should have been saying next. But here, this was an option of a box. Then after we call .asDref, we get an option of a reference. And then she has some tests for iterator. I'm sort of breezing through this because I just want to get to something more interesting next time. But I think the diversion was fine. And then let's make sure that only 2 things fail again. Only the 2 things that this is such a bad practice, but whatever. Okay, yeah, 9 passed, 2 failed. Hell yeah. So all this worked. Again, this is just really basic. Build a list of 3 items and then get things out of it. Next time we will, first I'll just say, she's very proud of the fact that so little of the code changed. Even though we changed the type of our node, or we changed the type of link, right? Link is now an RC, or an option of an RC. It was an option of a box. So little of our code changed, though, because Rust does the type inference, so we don't have to write types everywhere. So these, this function and this code, the iterator code, and some of this code didn't really have to change very much at all. I think, head looks a lot like prepend. Maybe it's identical. There's prepend. Not prepend. Head would look like peak, because peak is the thing that with the same type signature. Yep. I just named it, instead of first, I named it end this time. But it's exactly the same. We're calling slightly different code because the types are different, but the names of the functions are the same. So that's a beautiful thing about type inference. And then there's one last thing I wanted to mention. Oh, right. We only implemented one kind of iterator, but that's because none of the other kinds of iterators make sense. Our list shares its contents with any number of other lists through this RC. Whenever you do .tail, you get another list that just points one element into this list. Like she demos here. I created list 1, and then I call tail of list 1, and I get a new list, BCD, and all I did was I incremented the reference count to B. But otherwise, they share B, C, and D in memory. So because of that, it doesn't really make sense to own a list and to have an into-iter method that gives us, or an into-iter struct that gives us the elements by value. Because we can't actually pop things off this list anyway. We can only observe them. And of course, if we want to have the actual integers in the list, we can copy them out. But it's not like we're consuming the list, because the list might be sharing its data with something else. We can't just take ownership of the data. So that's why we don't have into-iter. We also don't have iter_mute for the very simple reason that you can't modify these elements, because otherwise it would break the sharing. The whole idea of the sharing is that none of us can modify anything in the list. So we can't have something that returns mutable references to inside the list, like iter_mute did, because we can't modify the list, right? We can't modify the elements in the list either. So that's all. Next time, I will go over drop, and next time will be at some point that I will schedule with a when to meet. It'll still be virtual, I think. Probably.
You think?
I will be back next week, but only for 2 days. But I'll be back a little bit later, and it could be that there's no interest. But you know, when we do that, I'll be picking up from here. But I'll also be willing to review anything for people who skipped a bunch.